Welcome everyone to GOCC today. We have Amy Bradford from the University of Texas at Austin, plus the University of Michigan, speaking to us about graph complexes and the study of cohomology of MGN. Before we get started, let me just remind you of our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So Amy, whenever you're ready.
Great, thank you so much. And thanks to Bailey and the other organizers for the opportunity to tell you what I think is like a really beautiful story that's connecting combinatorics and algebraic geometry, specifically in studying the moduli space of curves. And I'll also say that like if I'm very open to questions in the middle of this, so please just ask questions if you have them as we go along. So let me just say something about, okay, what do I want to like sort of get out of this talk? And so the main question I want to sort of answer and explore is like, how do we use this combinatorial object of graph complexes to help us study the cohomology of the moduli space of curves, which is this algebraic geometry space, the space in algebraic geometry that's like very, very well studied. And so the sort of goal is to sort of tie together these two notions. And if I may, I just want to sort of take a few minutes and remind or tell you about this moduli space of curves. So let me start off with the definition of this space that's the moduli space of curves. And so what we're going to do is we're going to define MGN is going to be a moduli space or a parameter space of, and I'll put in parentheses, isomorphism classes of smooth, projective, connected algebraic curves, which I'll always be working over the complex numbers today, of genus G with n marked points. And so let me just say something. This is a lot of adjectives that are just I'm throwing at you right now. And so if you've never seen the definition of a moduli space, what I mean about this is that I want to build a space that is going to be a parameter space for some geometric object of interest. So in other words, the points of my moduli space will point me to some geometric object of interest, and there should be some notion of close by points in my moduli space correspond to close by geometric objects, very roughly. And so the geometric objects I'm interested in are these algebraic curves. And there's a whole bunch of adjectives that we're throwing on here, but the two that I want to specify specifically are the connected and the smooth parts. So we're taking nice, smooth, connected curves, and then let me explain what the genus and the marked points mean in just a second. So let me just draw an example. So an example of this, the curve is going to be this one-dimensional variety or something that's built out of polynomials, but it's sort of exactly what we all sort of think of when we hear the word curve. It's just one-dimensional thing. And then what I mean when I say something that has n marked points, that just means I'm going to pick out some number of specified points on this curve, and I'm just going to label them. So something like this would be a 3 marked point because I've labeled 3 points on them. And I'll explain more about the genus in just a second. But basically, so these are the types of geometric objects I'm interested in. And so I'm building a parameter space whose points are going to correspond to these curves. So this is going to sit inside of the moduli space, the parameter space of genus 1, 3 marked curves. And again, I'll explain the genus in just a second. And so another perspective of this is coming from sort of complex analytic perspective. And it turns out that there's another way to sort of explain what this moduli space is. And this is like a very non-trivial statement, but it turns out to be true, that this moduli space is also the parameter space of, again, isomorphism classes of n-marked, compact, connected Riemann surfaces of genus G. So I can also draw a curve as a Riemann surface is sort of the point. So this is also going to be considered to be a curve. And then again, the n marked points is just going to be picking out a certain number of points that we're labeling. And now I define the genus G. I define the genus to be the genus of this Riemann surface. So the genus in this case is 1. And so I define the algebraic version of this genus to be the genus of the corresponding Riemann surface. So again, this is going to be sitting inside of M1, 3. Okay, and for the remainder of the talk, I'm not going to use the algebraic perspective as much as I'm going to use this Riemann surface perspective. But let's just like write down a few examples just so that we can get make sure we're comfortable with this definition. So this moduli space M03 is we're taking genus 0 curves with 3 marked points on them. And I want to build my moduli space to say, well, the points of this moduli space are going to correspond to isomorphism classes of genus 0 curves with 3 marked points. So we need to study what are all the types of curves that we can have that are of genus 0 with 3 marked points. Well, there's this really nice fact that if I have one of these genus 0 curves, there is always going to exist a unique isomorphism that takes the 3 points to 3 special points, 0, 1, and infinity. And so what this is saying is that if I hand you a genus 0 curve with 3 marked points, I can always construct an isomorphism to this very particular one. And so that means that there's only one isomorphism class, and so the moduli space is just going to be a point. Okay, and so let's move up. Let's add another marked point and see what happens then. So now I'm looking at genus 0 curves with 4 marked points. And again, sort of by the same theorem as above, I can always find an isomorphism that takes the first 3 points to these 3 very special points. And then this last point can sort of land anywhere I want on this curve. And so wherever I place this last green point, that's going to give me a unique special curve inside of this moduli space. And so I can parameterize this by saying, well, that last green point can land anywhere on this surface, which I'll denote as P1. So we can put this anywhere on this P1. But I don't want my marked points to collide. So in other words, I don't want this green point to land on any of these 3 special points. So I'm just going to take P1 and I'm going to subtract 0, 1, and infinity. And that's going to give me this description of M04. And we can like keep playing this game for the number of marked points with M0n. And you can write down nice descriptions, but maybe I'll write down one last example, which is this M11, which for anybody who's familiar with elliptic curves, this is going to be describing the moduli space of elliptic curves. And this is a very well studied subject, and it has a lot of combinatorial aspects about it already. But one thing that you learn if you study elliptic curves is that they're sort of parameterized by one number, which is its J invariant. And so the moduli space ends up being just a nice line that's parameterized by whatever this thing called the J invariant is of this curve. And so this is sort of as far as I can draw as examples go. If you keep going up in genus, the number of mark points, the description gets more complicated. But hopefully this is like enough to like get us on board with this definition. And so maybe before I continue, I'll see if there are questions about this definition here. Okay, great. And so one of the first things that you learn when you work with this moduli space is that you learn that it's not compact. So in other words, for an example, we could have a curve that sort of degenerates slowly into something like this. And this curve does not sit inside of MGN because it's not smooth. So this point right here is not a smooth point, it's a singular point. So I can have limits of smooth curves that are limiting to non-smooth curves, so it's not compact in this way. And so there's a way to fix this though, and so Deline and Mumford, they were able to give us a compactification of MGN. And so let me explain what this is. So we form a new moduli space, MGN bar, and what it's going to be, it's the moduli space of isomorphism classes of n-marked stable curves of genus G. So what is a stable curve? Well, number one, it could be smooth. So we're including all smooth curves. So in other words, MGN is sitting inside of MGN bar. But it can also include curves that are not smooth, but I'm going to be very careful about what kind of singularity I am involving here. So I can have singular curves or non-smooth curves, but the singularities need to be nodal. And what I mean by nodal is like in an example up here. So this point was not, this was like sort of the problem point of it not being smooth. And the nodal piece is saying that if I zoom in really close, it looks like an X. So that's what I'm going to include. I'm going to include all curves with singularities who have sort of this very simple type of singularity, which is nodal. And then I need to add in some technical condition that the automorphism group of the curve needs to be finite. It's not too important for the purposes of this talk, but we need to just include that in there. And so so what a nodal curve looks like in sort of the Riemann surface perspective is we take a whole bunch of smooth curves and then we connect them via the nodes right here. And some of them are self-intersecting and some of them are not. But this would be something inside of 7,4 bar, for example. And the really nice thing about when we sort of enlarge our moduli space to include these stable curves is that we already have quite a bit of combinatorial data popping out immediately. And so let's like zero in on that for a second. And so if I hand you a nodal curve, I can obtain some combinatorial data about that curve that just encodes the topology of it. And the way that we do that is we associate a graph to one of these nodal curves, one of these stable curves. And so how do we do that? Well, for every connected component, I'm going to assign a vertex to every connected component. For every node that sits in between two components, I'm going to draw an edge. So there's an edge here. There are two nodes connecting this one. There are three nodes that are connecting these two components and one node connecting these two components. And then finally, if I have any curves that have these sort of self-intersection nodes, I'm going to encode that with a loop. And so automatically, right off the bat, we sort of have the structure of how these connected components are attaching via nodes. And then I want to remember somehow that this has a genus. And so for example, this component right here was a genus 2 curve. So I'm going to weight my vertices. I'm going to weight this with a genus 2 and 0 and 3. And then I'm going to do something a little bit subtle, which is if I ever have a curve that has a self-intersecting node, for technical reasons, I don't want to assign this component a weight 2 vertex, even though it is a genus 2 curve. Because somehow I want the genus of my graph to match the genus of my curve. So the way that I'm going to fix that is if you ever see a component that has a self-intersection, I just pull apart the node. So I look at this bad self-intersection point and I just pull it up, and that will give me like a smooth genus 1 curve. And that's how I'm going to label this vertex, is the genus of the sort of pulled apart curve. And the reason that we do that is that we can define the genus of this curve then, or of this graph, to be the first Betti number of the graph. And then I'm going to add in a sum of all the vertices inside of my graph. And sum up all of the weights on the vertices. So in this particular case, H1 is going to be 5. And then we would sum up all of the weights on the vertices, and that's how I would assign a genus. And then it's a fact that if I do it in this way, that the genus of the graph will match the genus of the curve that I started with. So that's sort of why we want to do it. Okay, and so like this gives me like some very combinatorial data automatically when we're just sort of, we run into very naturally when we start studying this moduli space. And so like one example of this is if we tried to look at genus 1 curves with 2 marked points sitting inside of this compactification, what I would need to do is topologically, I would form every type of genus 1 curve that maybe has nodes that has 2 marked points on them and whose automorphism group is finite. And it just turns out that there's just not that many of them. So there are only 5 topological types of curves that you can have. And so like we get this very nice way of turning sort of a boundary stratification, or if I look at M12 bar, and subtract M12, then I can really encode this information just using these dual graphs. And so somehow graphical combinatorics is already showing up very naturally inside of the structure of this moduli space. And so now, like, let me give you one more example, which is going to be the example that we're focused on for the remainder of this talk, which is we're going to look at M3 sitting inside of M3 bar. So that is genus 3 curves with no marked points. And I've drawn out for you every single possible type of dual graph that is coming from this boundary stratification. And we'll come back to this visual, but the takeaway at this point in time is that we already have graphs and we already have combinatorics showing up very naturally in this picture. So let me shift gears and say something about the cohomology of this space. So first of all, this has been a very well-studied space in a lot of different areas of math, and the cohomology is quite mysterious, and it's quite a hard problem to sort of compute the cohomology of this space. And there are a lot of different techniques that have been developed over the years, and some of them are really useful in some ways, and then they're not very useful in other ways. And so what we're going to do for the rest of the talk is sort of explain how we can use combinatorial methods to get at the cohomology of this space. And it turns out that like studying the full cohomology ring is sometimes too ambitious. And so the first thing that I want to say is that we're not actually going to study the full cohomology ring, but just a piece of it. That's sort of the goal today. And so this is encoded in the sort of notion of a weight filtration. And so what this is that Deline gave us this very nice perspective in which he said that if we take X to be a topological space that is in addition a complex variety, so it has the structure of coming from polynomials in some way, then the cohomology of that space has a nice canonical filtration. And so what do I mean by that? Well, we have like the full cohomology ring sitting here, but I can filter it into smaller pieces. And so I'll write this out and then I'll say something about it. So we can filter it all the way down. And a lot of times it's easier to study these individual pieces instead of the entire cohomology ring itself. And so this is like a structure that's like very specific to the field of algebraic geometry. You don't get this unless you sort of have a topological space that is in addition a variety. And so for us, what we're going to do is we're going to let X be this space that we care about. And what we're going to do is we're really going to study sort of the bottom piece of this filtration. And it turns out to be a bit easier to get our hands on than just the full ring itself. And so let me make one more definition, which is the jth graded piece of the cohomology. And all we're going to do is I'm going to define this to be the weight j piece quotiented by the weight j minus 1 piece. Okay, and so for the remainder of the talk, what we're really going to be focusing on is j equals to 0. And in that particular case, that's just equal to the weight 0, so sort of the very bottom part of this filtration of the cohomology. So this is sort of the goals, is to say something about this. And right, and so it turns out that there's this very tropical combinatorial perspective on how I can attack this problem. And so that's what I want to sort of spend the rest of the talk on is saying something about this graph complex perspective. But before I do that, what I really want to do is sort of show you how useful it is to use combinatorics in this problem. And to do that, I want to just say a few words about how you would study this space in like a purely algebraic way for the purposes of showing how well combinatorics can help us reduce this problem. And so I'm going to sort of float over the details. The details aren't super important, but I just want to sort of really ingrained that combinatorics is very, very helpful in this kind of problem. So let me say something about how we could go about studying the kth graded piece of a cohomology.
Hey,
And again,
Amy.
yep.
Oh, sorry, quick question. So Deline's theorem, this is only for compactly supported
Oh,
cohomology?
good question. Yeah, so I have compactly supported cohomology here, but you don't need it. It can
Okay.
be singular, it can be different types.
Okay.
Specifically, our theorems are just associated with the compactly supported. But yes, thanks. Yeah, good question. Yeah. Okay, and so Deline also gives us a way to like expressly compute this graded piece of the cohomology. And let me just tell you sort of the algorithm for how we can do this. And so it turns out that this kth graded piece, we can turn this into studying a complex. So it turns out that the kth graded piece is going to be, or maybe I'll just say, is the cohomology of the following complex. So here's sort of the algorithm for which we go about to sort of study this space. So the first thing that we do is we write down all of the dual graphs in this boundary. And then what we're going to do is we're going to sort them according to the number of edges. And so in this example, and sort of this running example that we're doing, this is for M30, and these are all of the dual graphs, and I've already sorted them according to the number of edges in the dual graph. So that's the first step that you would do. And then the next step of what we do is we build the following complex. And so the first thing that we do is I write down every graph that has 0 edges. That's sort of the first piece of this complex. And it turns out for every single case, there's only one graph that's going to have 0 edges, which is one vertex of genus G and then however many marked points you had. And then what we do is if I want to build H or the kth graded piece, then I'm going to build this out of HK of, let me write it down, then I'll explain, of this M gamma bar. So what is this? So I'm letting this graph be gamma, and then I'm saying, let's collect every single curve inside of MGN bar whose dual graph is this very particular dual graph gamma here. Let's collect all of those together. And that is what this M gamma bar is. So it's sort of the moduli space of curves whose dual graph is gamma. And then I can close it off. That's something I can do. And that's sort of the first piece of this sequence. And then like we keep going and we build this sequence now, and I build it up over dual graphs gamma whose number of edges is 1. And I take a direct sum of these things. And so now we can have graphs that look like this, or graphs that look like this. And we can have a whole bunch of them. And again, we're going to just build HK of the moduli space of curves with these particular dual graphs. And I'll also say that whenever we're doing moduli theory and algebraic geometry, or kind of anywhere, you're worried about isomorphism classes of objects. And so I don't actually want to take the full ring here, but I need to be really careful about whether or not my graphs have automorphisms or not. And so again, like the details of this are not too important. But what I'm going to do is I'm going to take a subring of this that's just aught gamma invariant. And you proceed forward and you keep doing this. And so you keep doing this for edges that are 2 and then 3 and then 4 and etc. until you run out of terms. And then it turns out that the cohomology of this complex is going to be exactly what we want here. And so let me just like show you what this type of complex looks like if I wanted to compute weight 0 of M3. So this was what our running example is. So, oh, sorry, let me just continue. So this is just saying that if I want to compute weight 0, then I just replace all of the k's in my complex with an H0. But essentially, this is the complex that you get. If I want to compute weight 0 of M3, this is algebraically how I would do it. And this is really messy and kind of scary to look at, in my opinion. And you can imagine that if I get into more complicated cases, this is going to be really big and really unmanageable to actually do computations with. And so what I want to do now, so sort of the moral of that whole story is that there is a way that I can algebraically compute this cohomology. It's rather nasty though. And so now what I want to do is let's shift and let's look at graph complexes instead. And let's just try and see if we can reframe this in a way that's more approachable. And so let's just move finally just into the combinatorics. And so what I'm going to do is I'm going to build a graph complex for you. And so underlying this graph complex is going to be this vector space, which I define F, H, M bar, Gn. And so what this is going to be defined as is it's going to be a rational vector space generated by the following. So it's going to be generated by pairs gamma, omega. And in this case, gamma is going to be a stable graph. So in other words, it's going to be one of those dual graphs that we've been seeing all along. So this is a stable graph of genus G with n marked points. And then I'm also going to add in the condition that I'm going to allow extra decorations on my graph. So we're not just looking at graphs themselves, but we're also going to allow decorations on these graphs. And so I'll also say gamma is, or maybe the vertices of gamma are decorated appropriately with some cohomology classes. Which I'll do an example below to make this hopefully clear. But what we're starting out with is we're just going to take some sort of a stable graph, and then we're going to add on some extra decorations. And then this omega piece is going to be an orientation of our graph. And what I mean by that is it's going to be a total ordering of the edge set. And so, for example, let's look at something like this. Let's look at an undecorated graph for a minute. So I could take one of these graphs with these weighted vertices, and then this omega is just going to be, I'm going to totally order the edge set in some way. And then I have to say something about, well, what if I take a graph and I order it in a different way? So I actually want equivalence classes in this vector space. So I say subject to the relation that if I orient gamma in one way, so if I totally order it in one way, how is that related to totally ordering it in another way? Well, in this particular example over here, I could have also chosen this top edge to be 2 and this bottom edge to be 1. And so if I reorder my edges, I can relate them via some permutation. So I permuted the edges around. I turned 1 into 2 and I turned 2 into 1. And so I'm going to say that these two elements in this vector space are equal up to some sign. And this sign is going to be this sigma is going to be the permutation that's permuting my edges. And then I just take the sign of that permutation. So in other words, in this vector space, these two are equal up to a sign. Okay, so that's all we're doing right now is we're taking a vector space that's generated by a certain type of graph. And so let me write down another example that's including these decorations. So let's do a bit more of a complicated example. So we have this graph right here. And then I have some weights on my vertices. So this is like weight 2, 0, 1, and 4. And then I need to totally order my edge set in some way. And then the final piece of information that we haven't talked about yet is, so we have the stable graph, we have the orientation, and then I need to tell you what I mean when I say decorate the vertices with some cohomology classes. So let me kind of zoom in to this picture right here. And so on each vertex, I'm going to not only have a weight, but I'm also going to have an extra decoration. And this decoration is going to be any element of some cohomology class of a particular moduli space. And so what I'll label this extra decoration on this vertex is I'll say this is alpha inside of H6 of, okay, which moduli space do I pick? Well, I'm going to use one of my moduli space of curves. And then what I'm going to do is I'm going to say which one. I'm going to say this is M, and then I look at the weight on the vertex 2. And then I look at the valence of that vertex, which is 3 in this case. So at each vertex, you zoom in really close. You look at the moduli space of the weight of that vertex, with the number of marked points being the valence. And then I'm just going to pick any cohomology class I want from that moduli space, and I'm just going to decorate it formally with some symbol. So let's, for an example, in this case, this would be some cohomology class inside of M03, because again, this is weight 0 and the valence is 3. At this one, I could decorate it with an element of H2 of M15. And then this last guy, let's slap a decoration on that's from H4 of M47. So like formally, all we're doing is we're taking one of these graphs and then I'm just attaching a cohomology class to each of the vertices. That's really all that I'm doing right now. And let me make a note, which is very useful when we're using this sort of graph complex perspective. So because of this relation right here, if there is an automorphism of gamma that induces an odd permutation on the edge set, then it doesn't matter what orientation I put on it, this class is going to be 0 inside of my vector space. So for example, this guy up here that we did as our first example, whenever you have a parallel edge, there's always going to be an automorphism of a graph that flips those two edges. And the permutation is just flipping the two edges, and so that's an odd permutation. So anytime I have a multi-edged graph, that's just automatically going to be 0, and that's due to some technical condition on how we're relating this via a sign. And so this is quite useful, and we'll see like why this is useful in just a second. But I just wanted to make that note right now. And so let's just proceed though. So these are the elements of this vector space. And then what I want to do is I want to say something a little bit more refined than just this full vector space. So I can define a weight of a graph in this vector space, and we're going to define this to be the sum of the degrees of the vertex decorations. So if we come back, or maybe I put it forward here. Yeah, so this was the graph that we had in our example. And then what I'm going to do to say what is the weight of this? Well, we're going to pick out the degree of the cohomology classes on each of the vertices, and we sum them up, and that's going to be the weight of a graph in this complex. And so I can gather together then. I can say, well, now I just want to restrict my attention to weight k graphs or something like that. And so this is going to be the complex that I actually want to work with. This is the Getzler-Kapranov graph complex. And so what we're looking at is this is going to be sort of weight k. And because I can do this, I can tell you like a weight k graph is going to be, where all of the sum of the degrees of the decorations are going to be k. I can do a sort of a similar notion to what we talked about before, and I can take quotients. I can take the weight k piece quotiented by the weight k minus 1, and that's going to be this graded piece. And so again, for the rest of this, we're going to really be focusing in on the 0 piece here, which is going to just be any sort of graph inside of this complex whose vertex decorations add up to 0. That's all we're saying now. Okay, and so this is this definition that we're really caring about right here. Okay, and so what does this look like if I want to say, what does a weight zero graph look like inside of this vector space? Well, here's an example, is that we can take any sort of sum of graphs, and then what I need to do is I need to specify that the weight is going to be 0, and so I need to put a cohomology decoration on each of these vertices whose degree sums up to 0. There's only one possible thing that I can do. I can only put elements of H0 on here. So for every single vertex, the decoration is going to be an H0 of one of these MGN bars. And so, this is the part that we're going to use at the very beginning when I said that MGN bars, these are all connected. And so because of that, H0 is just going to be a copy of Q. That's all that we're saying here. And so really, if I'm decorating something with an element of Q, I can just sort of say, well, just let it be 1, you know, the number 1. There's no interesting cohomology in degree 0 of these moduli spaces. And so I might as well just sort of ignore the decoration, if you will. So in the future, what I'll do is I'll write an element of this graph complex secretly. We are decorating each vertex with an element of H0, but you know, there's sort of nothing interesting to be said. So we can actually sort of consider this weight 0 complex to be, ignore the decorations, just look at the combinatorics of the graph. So really, we're just building a nice, simple combinatorial vector space full of these undecorated graphs. Um, and not only is this a vector space, but there's an appropriate notion of a differential. And so if I sort my graphs according to the number of edges, then I can create a differential. And the differential is going to be as follows. So if I hand you a graph of a certain number of edges, and I want to map it into the set of graphs with one more edge, one way that I could do that is I could sort of add an edge in every single possible appropriate way. So that would be looking at a vertex and like splitting it and creating a new edge, or creating a loop at different vertices. And so again, it's not too important for the purposes of this talk for this to be specific, but really what I just want to impress upon you is that like this is a differential graded vector space. And so in other words, we can form a graph complex. There's some notion of a differential, we can form a complex. And so let's get back to MGN now. And this is sort of the big theorem that is quite remarkable, is that if I take the cohomology of a graph complex, the one that we just defined, this is isomorphic to the kth graded piece of the cohomology of MGN. And so what this is saying to us is that I gave you one way of computing this, and it was very hand wavy and it was very algebraic, but ultimately it gave us this very messy expression, right? But now what this theorem is telling us is that I can actually ignore the algebraic expression. I can just look at my graph complex and I can look at cohomology there. And so as an example, if we want to, again, find the weight 0 cohomology of M3, then what this is saying is that it will be the cohomology of this particular graph complex. So of genus 3 decorated graphs of weight 0. And this is what this complex looks like. And this is much simpler than this guy. So somehow these two complexes are giving us the exact same information. And this version is much easier, number one, to like comprehend, to sort of get our hands on. And so like just visually, it's already better to sort of go with this graph complex perspective. And the really cool thing about graph complexes is that they've been studied independently from this problem for a long time. And so there are actually even more reductions that we can do to help us just using a combinatorial perspective. And so, for example, let me define for you one more type of graph complex, which is very similar to the one we just said. So what I'm going to define is this GK0 bar. And what we're going to do is we're going to pick out these decorated oriented graphs, but we're going to make sure that the weight on each vertex is 0, so I can't have positive genus vertices. And I'm also going to make sure that my graphs don't have any loops. So that's just some sub-vector space of this vector space formed of these graphs. So we're just eliminating positive genus vertices, and we're eliminating loops. And this theorem from Sam Payne and Thomas Vilvacher tells us that the cohomologies match. And so in other words, if I come back to this expression, and so the ultimate goal again was to compute the weight 0 piece, which we said was the same as computing the cohomology of this complex. What I can actually do now is, since these cohomologies are equal, I can just eliminate all of the graphs with positive genus vertices and with loops. And so I can just pictorially say anything with a positive genus vertex has to die in this graph complex, and anything with a loop has to die inside of this graph complex. And so only one thing remains when I do that. And so what we've done is we've taken this giant algebraic expression here, and I've turned it into this very, 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 very simple complex here. And we've said the cohomology of this computes this, and this is like automatic. I can say that the weight 0 cohomology then is non-zero, and graphically I can say it's represented by this graph right here. So you can like sort of visually see this huge process of we took this algebraic expression and we shuffled it down, and we got something that was very manageable. And so what I'll say sort of to finish off this talk is like, how did this help us get progress in computing the cohomology of MG? And historically, computing even degree cohomology has had better results than computing odd degree cohomology. So for example, the first example of a non-vanishing odd cohomology group was found in 2005, and then it was just blank for years. And then Sam Payne and Melody Chan and Soren Galatius were able to use this graph complex method to compute 3 new non-vanishing odd cohomology groups. And it was also very impressive because they were able to sort of disprove long-standing conjectures in this field as well. And then they kept pushing it. And so now we actually have infinite families of non-vanishing odd cohomology groups that were all sort of within the last 5 years, this has sort of been pushed. And so this is like really cracked open this field quite a bit by just like looking at this combinatorial perspective. And so this is sort of summarized in this chart here, where this is the, each entry is going to be telling you the dimension of the weight 0 piece of this cohomology. And this has been well studied from a long time, and a lot of different people have contributed to this chart. But this sort of green and orange piece right here is coming from this graph complex perspective. So it's really given us a lot of information and improvement in this field. And then the last thing that I'll say is that you can also apply this to other moduli spaces. It's not just the moduli space of curves. We can use this sort of graph complex perspective to make progress in other moduli spaces. So one example is the moduli space of abelian varieties. So if you know about this, this is yet another very, very well studied space in algebraic geometry, and it's related to MG in some very nice way. And you can use same techniques here, and you can, and there's been a lot of progress in computing the cohomology here. And then finally, sort of the last space I'll talk about is the space that I'm interested in, which this is the moduli space of curves of a specific type, which are called of compact type. And this is something technical, saying that the dual graph of a curve has to be a tree. But the point is that somehow MG and AG are very well studied in algebraic geometry, and this moduli space sort of sits in between them and is able to help us communicate between them. And so what my research is studying on is really looking at this guy and using these sort of combinatorial techniques similar to what I've just presented to say something about this other moduli space. Yeah, I think that's all I had. Yeah, thank you.
Thank you so much, Amy, for such a great talk. We'll open it up for questions. Does anyone have any questions? Okay, I might have two questions. So, towards the end, there was the moment due to the Payne-Billwacker result where you were able to like eliminate all the graphs that had loops or the labels
That's
that
right.
exceeded 0. So why was that again? This was, or maybe you can show the result again from 2024
Yeah, so let's
Payne-Billwacker.
go back. So the result from 2024 is saying that
Mhm.
if I construct a complex that has no loops and no positive genus vertices, then it turns out that the cohomology of that space is the same as the cohomology of the other space, essentially. And so this is just saying, because of this result, I can delete any graph in my
Mhm.
complex that has a loop or has a positive weight.
Okay. And was there a way in which, so you were computing, this was all to compute the like compactly supported cohomology. Is there like a combinatorial sort of analog or like interpretation of the compact support, or was there any kind of combinatorial restriction that was encoding sort of the
That's a good question. So like another way that you can phrase this in combinatorics is looking at it through tropical geometry, if anybody's interested in that. And so you can sort of use the same sort of perspectives to understand the cohomology of tropical moduli spaces. And so that's kind of a combinatorial perspective. Other than that, I'm not sure about the rest. Yeah.
I would maybe have one more question. So it seems that, and correct me if I'm wrong, but it seems that cohomology of MGN has been much more elusive than the cohomology of MGN bar. Or we historically have known a lot less, or it's been harder to compute. Is there like, if this is true, is there like maybe a philosophical reason for this sort of comparing?
Yeah, so I'll say that like somehow this is kind of a cool field of study because there are ways that you can transfer information between MGN and MGN bar. And so I don't know if necessarily one is easier or harder than the other one, but if you get some result on some side, there's some machinery that you can usually push it through to get something on the other side. So I would say that they're probably somewhat equally difficult, if you will, but
Mm,
it definitely gives you they react a lot together. So
awesome. Thank you. Any other questions for Amy? Okay. Well, thank you so much again. I'll go ahead and stop the recording.